This video clip is going to focus on the concept known as reaction spontaneity, or what can we do to predict if a reaction will or will not occur. Reactions can be predicted as to be spontaneous or not using something known as Gibbs free energy, or delta G. In working with Gibbs free energy, several factors influence if a chemical reaction will occur. And if a reaction occurs, we say that that reaction is spontaneous. One thing that will influence if a reaction occurs is the delta H of reaction, or the enthalpy of reaction. A second thing that influences if a reaction is spontaneous or not is the change in entropy of the reaction. Is the reaction becoming more ordered or more disordered? A third factor that influences reaction spontaneity is the temperature. The absolute temperature under which the reaction is occurring is essentially a measure of the kinetic energy available to the reaction. So we have delta H, delta S, and temperature all work in concert to determine how much free energy is available to cause a reaction to occur and be spontaneous, or to not occur, which would be a non-spontaneous reaction. If we combine delta H, delta S, and temperature, that gives us the Gibbs-Helmholtz equation, which is used for predicting reaction spontaneity. The Gibbs-Helmholtz equation is delta G, or Gibbs free energy, is equal to delta H minus T delta S. Delta G, or Gibbs free energy, is essentially a measure of the amount of energy available to do work, or to make a reaction happen, or in some cases to not occur. Let's start for a moment. Let's consider change in enthalpy and entropy for a reaction. Now, nature has certain preferences for enthalpy changes and entropy changes. Let's start by focusing on our change in enthalpy for a reaction. In our picture, this would be an example of an exothermic process, that we're starting at a higher energy going to a lower energy. Our delta H here would be a negative, and the process is exothermic. Now, nature prefers movement from high energy towards lower energy. This would be why, for example, when we trip, we fall down. Why water flows downhill. In both cases, something is moving towards a lower state of energy. So you could say here, Mother Nature prefers, when we have an exothermic process and we have a delta H that's going to be a negative number. However, in an endothermic process, when we're moving from a lower energy state to a higher energy state, and delta H is a positive number, under these circumstances, Mother Nature does not particularly prefer going from a low energy to a higher energy state. This would be an unpreferred direction by nature, the endothermic process. Taking a look at delta S, or change in entropy, the preferred direction by nature is towards more disorder. Consider, for example, something we're familiar with, such as a house. Over time, if left unattended, the natural flow would be for the house to move to a state of disorder. The brickwork would crumble, the paint would peel, the grass would grow, and we'd move to a greater state of disorder. So the natural flow in the universe is towards things go from a state of order towards more disorder. So the preferred direction by Mother Nature for entropy is towards greater disorder, which would be a positive value for our change in entropy. Whereas Mother Nature frowns upon, in the direction of something going towards a lower state of entropy or more order, and something a negative value for delta S is frowned upon by Mother Nature. Next, now let's take a look at how delta H and delta S and temperature all combine to influence if a reaction will occur or not, and how we can use this to predict if a reaction will be spontaneous. First, let's focus on conditions where both delta H and delta S are preferred by Mother Nature. In the case of delta H, Mother Nature prefers the reactions that are exothermic, going from higher to low energy, so our value would be a positive number. Delta S, Mother Nature prefers when the entropy is increasing, which would be an increase in disorder. This is reflected by a positive value also for delta S. Oops, let's switch this back here. Our exothermic, actually, that's a negative value for our delta H when we have an exothermic. When our entropy or disorder is increasing, we would have a positive value for our delta S. Now the temperature scale that's used in this calculation is always going to be temperature in Kelvin. Now one of the things about the Kelvin temperature scale is the temperature is always going to be a positive value. There are no negative Kelvin temperatures. Now first, just conceptually, if we consider that Mother Nature prefers both exothermic processes and entropy increasing, with this combination where both factors, enthalpy and entropy, being preferred by Mother Nature, under these circumstances a reaction is going to be spontaneous. In fact, under these circumstances, the reaction will always be spontaneous when it's an exothermic process with an increase in entropy. Next, let's take a look at this just mathematically, the implications of having an exothermic process with an increase in entropy. By exothermic, this number always has to be negative for delta H. Increased in entropy, we always have a positive delta S. Kelvin temperature scale, the temperature is always going to be positive. We have a subtraction in here as part of our Gibbs-Helmholtz equation. The temperature is multiplied times the entropy. Now mathematically, if we consider a positive temperature times a positive delta S, this number is always going to come out to be positive. Here we have a negative for our delta H. We're subtracting from it a positive number. No matter what the size of either of these numbers, our delta H and delta S, taking a negative and subtracting from it a positive is always going to give us an answer that's going to be negative. Now conceptually, because we have both conditions being favorable by nature, both the delta H, delta S, tells us the reaction is going to be spontaneous, what we can say now is if we have a delta G with a negative value, that tells us the reaction will be spontaneous, or it will occur under those conditions. Now let's take a look at the flip circumstance where both the delta H and the delta S are unfavorable with nature. An unfavorable delta H would be the process where it's endothermic, and we'd see a value for our delta H that's positive. An unfavorable condition for our delta S would be a decrease in the entropy, or where something's getting more organized or more orderly. This would be reflected by a negative value for our delta S. Now, under this circumstance, conceptually, where we have both things being unfavorable, both the delta H and the delta S, this would give rise to a reaction that's going to be non-spontaneous. In fact, under these conditions, the double thumbs down from Mother Nature, this will be a circumstance when the reaction will always be non-spontaneous with a double thumbs down from Mother Nature. If we take a look at this now mathematically, our delta H is always going to be a positive for endo. Temperature is positive for the Kelvin scale. Our entropy is negative for a decrease in our amount of disorder. Entropy and temperature are multiplied together, and we have a subtraction in here for our Gibbs-Helmholtz equation. Multiplying the positive times the negative for the temperature times the delta S is going to give us a number that's negative. We have a subtraction, we have a positive. Because we're subtracting here a negative number, essentially it makes it as if we're adding some more. So now if we have a positive number and we're adding to it another number, no matter what we do mathematically, the answer has to come out to be a positive result. This would give us something where it's a non-spontaneous reaction. And what we know now is that if we get a positive value for our delta G, that indicates that the reaction under those conditions is going to be non-spontaneous or will not occur. Now, it's possible in some reactions where we have one thing that's favorable. For example, the delta H is exothermic, but the entropy change is unfavorable, where it's getting, say, more orderly. Under these circumstances, it depends on such things as the temperature or what the size of the entropy change may be to predict if the reaction will be spontaneous or not. Let's use an example to illustrate this. Just the process of liquid water turning into solid water. Now, since solid water is at a lower state of energy than liquid water, our process here, our delta H for this process would be negative, and the process of water turning from a liquid to a solid would be exothermic. The exothermic process here is something that would be favored by Mother Nature, going to a lower state of energy. The entropy change is also a drop, where our delta S is negative as we're going from a more disordered form, liquid water, to a more orderly form, solid water. So there's a drop in the entropy. This would be something that is unfavorable by Mother Nature. She does not prefer going to a more organized state. Now, this process of water freezing, if we take a look at this, what we can see is that with our temperature, which is positive, times a negative entropy, that's going to give us a negative number. With our subtraction in here, we have a minus for our exothermic process. Now, having the minus minus here gives us essentially as though we're adding a number on. So what will influence whether this is spontaneous or not would be the size of our temperature value. For example, the process of liquid water turning into solid water at 25 degrees Celsius or room temperature, this would be something we would say is non-spontaneous. And being non-spontaneous, the delta G we get for this would be a positive number. However, merely change our temperature, change the temperature to say negative 10 degrees Celsius, and now a process of our liquid water turning into solid water most definitely becomes spontaneous. And with the reaction being spontaneous, this would indicate that our delta G would come out to be a negative number under these temperature conditions.